Good morning and welcome to section 4.3. Today we're going to look at how derivatives affect the shape of a graph. So we're going to be looking at first and second derivatives and how you can use that information to know what the graph of a function would look like. So the first thing we're going to look at is how do you know if a function is increasing or decreasing? Well, when you guys first started pre-calc or even algebra 2, you talked about you know what slope is. If you have a positive slope as you read a graph from left to right, you're increasing, and if you have a negative slope, you're looking at a graph, as you read a graph from left to right, it's decreasing. That's true about derivatives. The derivative is the slope of the tangent line. So if you have a positive first derivative, it means that you are increasing. If you have a negative first derivative or slope of your tangent line, it means it's decreasing. So let's just look at it. From A to B, I would say we are increasing, okay? And if you look at all your tangent lines, the slopes of those tangent lines are positives. Okay, and then from B to C, you would notice that you're decreasing, but your tangent lines also have negative slope. Tangent lines are your derivatives. And then from C to D, we're increasing. One thing I would take note of is how do you go from increasing to decreasing or decreasing to increasing? You got these slopes of 0. Okay, so we found these in section 4.1. When you find your first derivative and set it equal to 0, those are your critical points. Or I should say critical numbers. They're not points until you find the y value, but those are your critical numbers. So usually we use those to decipher or, let's say, plot out or break apart, that's the word I'm looking for, when you go from increasing to decreasing. So here's an example. Find where the function is increasing and where it is decreasing. So the first thing we're going to have to do is go ahead and take our derivative. Okay, that's going to find where we are switching from increasing to decreasing using our critical points. So our first derivative, we'd have 12x to the third minus 12x squared minus 24x. Go ahead and set that equal to 0. Then we have to solve the right-hand side. So what we're going to do is we're going to go ahead and factor out the 12x. So we have x squared minus x minus 2. And then I can factor my quadratic even further, x minus 2, x plus 1. Now we're going to go ahead and set each part of that equal to 0. So 12x equals 0, x minus 2 equals 0, x plus 1 equals 0. Okay, so x equals 0, x equals 2, and x equals negative 1. All of these, that's a negative 1, all of these are our critical values. Okay. They could be max and mins, but we don't know exactly at this moment. Critical values. So it's not asking us just to find our critical values, though. It's asking us to find when we are increasing and where we are decreasing. So what we're going to go ahead and do is make ourselves a number line. Okay. And on our number line, we're going to go ahead and write down our critical values. So we'll have negative 1, 0, and 2. And then what we're going to do is we are going to test points. Okay, the points we test, we are going to go ahead and plug into our derivative. So f prime of x, we're plugging those numbers into here. So I'm looking at a number less than negative 1, in between there, and then in between 0 and 2. So I'm going to plug it into actually this, my factored form, because I like to think about things in terms of positives and negatives. So I'm going to go ahead and plug in negative 2. So we're going to think, what if x is negative 2? I plug it into my derivative. I would have 12 times negative 2, that's some negative number. Negative 2 minus 2 is another negative number. Negative 2 plus 1 is another negative. So negative times negative is positive. Positive times a negative will give me an overall negative answer. Negative number. If my derivative is negative, that tells me I am decreasing. So it's a negative here. Then we're going to go ahead and plug in a number in between negative 1 and 0. So I'm going to do x equals negative 0.5. So 12 times a negative is going to give me a negative. Negative 0.5 minus 2, another negative. And then negative 0.5 plus 1 is a positive. Negative times negative, positive. Positive times positive is a positive. Then I'm going to go ahead and do in between 0 and 2. This will be positive. 12 times 1 is positive. 1 minus 2 is negative, and then positive. So if I do 1, we had positive, negative, positive, which gives me an overall answer of negative. And then number bigger than 2, 3. Positive, positive, positive. They're all positive, which means it's overall positive. Okay. Now I can use this nice little graph to go ahead and, or not graph, but table, to help us say where we're increasing and where we are decreasing. So our answer, increasing. We write our answer in interval notation, and it's from -1 to 0, union 2, and all the way on to infinity. The reason they are parentheses is because these are our critical numbers, and either there you're neither increasing nor decreasing because it's a max or min. So there's our increasing. Then we're going to write down decreasing. So negative infinity to -1, union 0 to 2. Okay, so that is increasing and decreasing. So the first derivative test. Some things we need to look at is that suppose that c is a critical number. So you took your derivative, set it equal to 0, and c is one of those values that we just wrote on our table here. That's what they're saying c is. Okay. If f changes from a positive to a negative at c, sorry, f prime, your derivative changes from positive to negative at c, then f has a local max. So let's think about it. If I go back here to this picture, we are going down and then we're going up. Well, that makes sense that this should be a minimum. Oh, sorry, I was looking at the wrong, I didn't do positive to negative. If we do positive to negative, that's going to be this section right here. We're going positive to negative. If I go positive to negative, then I could conclude that at 0, that is going to be a maximum, and same vice versa for negative to positive. Okay, so that's what this is telling us here. If our derivative changes from a positive to a negative, so we're going from a positive to a negative, then it's a max. If it goes from a negative to a positive, then it's a min. If f does not change signs at c, so if it said positive, sorry, f prime, our first derivative, if it says positive, positive, negative, negative, that is an example of a no local max or no local min. Okay? So here we'd have our point c, and here we'd have a positive, and then we'd have a negative. So positive, negative, that gave us our local max. This next one, at my point c, I had negative, and then I had positive, so that would be a minimum. Now when I get to this example for C, I have positive, 0, and then positive again. So since it's positive, positive, there is no max or min. And then C one last time, we are negative, 0, negative, so negative, negative. So since there is no change, there must be that sign change, then there is no local max or local min. All right, so here's an example. Find the local max and local mins of the function g of x on 0 to 2 pi. So since it's telling me 0 to 2 pi, I know I must be in radians. So I'm going to go ahead and find my critical numbers by taking the derivative. So g prime is 1 plus 2 cosine of x. Now we're going to go ahead and set that equal to 0. I'm going to subtract 1 and divide by 2. So cosine of x equals -1 over 2. All right, if you are not good with your unit circle, you could do this on your calculator. Make sure you're in radian mode, but you're going to do cosine inverse of -1/2, and then you'd have to figure out, is that pi over 6, pi over 4, pi over 3? Okay, and then figure out if it's which quadrant it is, if it's not one of those, okay? So we know cosine, thinking about our unit circle, that is going to be your x values. Where are my x values negative? Well, in quadrant 2 and quadrant 3. And then where would it be 1/2? Well, if I think about it over here, it's actually at pi over 3. So then how do I go over here? Okay, well, what would this value be? This is at 2 pi over 3. And then you have to find the other one. So this is going to be 4 pi over 3. Okay, so you could think about it in terms of quadrant 1 and then say, but I need a negative, so that means I got to be in quadrants 2 and 3, and you can go from there. So our answers here are at x equals 2 pi over 3, and 4 pi over 3. And if you need to use your calculator, you can. You're just going to need to know how to figure out what the exact answer is in terms of radians. So what are these numbers now that I have them? These are our critical values. So what we're going to do is I'm going to put these on my number line. So we got 2 pi over 3 and 4 pi over 3. And then what we're going to do is we're going to plug those numbers in between there into our derivative. So when I plug them in, a number less than 2 pi over 3, I'm actually going to go ahead and do pi over 3 because we know what this value is for, oh, it's cosine though. Yes, cosine, pi over 3. This is going to give us positive 1/2. So I plug it into here. My g prime of pi over 3 will be 1 plus 2 times cosine of pi over 3, which is 1/2. This is going to give us 1 plus 1, so 2, which is a positive number. Okay. What would be an easy number to check in between here? I would say probably pi. Okay. So if I do g prime of pi, I'll have pi plus 2 times cosine of pi. So I'm plugging in here. Cosine of pi is your y value, and here it's -1. Okay. Did I write something down wrong? Let's see here. (3.14) minus 2. That'd be a positive number. What did I do? Let's see. Oh, why did I plug in pi? What should this be? This should still be 1. I was thinking it was an x, but I was mixing my functions. So be 1. There we go. This should be 1 minus 2 times -1. Ah, this is a positive 2. So plugging in this, 1 plus 2 cosine of pi is -1. So I really have 1 minus 2, which is equal to -1. So that's negative. And then a number bigger than this, I'm going to do 2 pi. So g prime of 2 pi. So I'll have 1 plus 2 times cosine at 2 pi. So your x value here is just 1. So I have 1 plus 2, which is 3, so it's positive. Okay. And now it's not telling us to say where increasing and decreasing is, but I would say it's telling me from 0 to 2 pi. So if you wanted to write down increasing and decreasing, you'd be increasing from 0 to 2 pi over 3, union 4 pi over 3 to 2 pi, and then you'd be decreasing on this interval. But it's just asking us to find local max and mins. We can only conclude local. We cannot conclude absolute using this method. So we are increasing and then we are decreasing. So that would imply that at 2 pi over 3 there is a local max. And then at 4 pi over 3 we are decreasing and then increasing, so this would be a local min. Okay, so at those values you would have those answers. All right. Next one says, find where the function is increasing, decreasing, and any local max or min. So we're going to do the same method. We need to know where our critical values are, so we are going to find the derivative. Derivative 2 is 0, so we have 4x minus 4x to the third. Set it equal to 0. Factor out a 4x. Be careful, it's really going to be 1 minus x squared. Then I'm going to do a GCF, or not GCF, difference of squares. So it's 1 minus x, 1 plus x. And then we would set them each equal to 0. So x equals 0, x equals 1, x equals -1. Then I'm going to go ahead and create a number line with those numbers on there. So we will have -1. 0, 1. And then we just need to remember we're plugging them into our derivative. Okay, so this is our derivative. So if I plug in these numbers to our derivative, a number less than -1 would be -2. If I plug in a -2 here, 4 times a -2 is a negative. 2 minus a -2 actually be a positive. And then I would have -1 plus a -2, so it's negative. So overall, my answer will be positive. Okay, then I'm going to go from -1 to 0. I'm going to plug in -0.5. So that'd be negative. 1 minus a negative, so plus. And then 1 plus a -0.5 would be a positive. So this one gives me a negative. Then I'm going to plug in a number between 0 and 1. Think about 0.5. 4 times 0.5 is a positive. 1 minus 0.5, positive. And then 1 plus 0.5 is a positive. They're all positive, so positive. And then lastly, a number bigger than 1, 3. That'd be positive. 1 minus 3, negative. 1 plus 3, positive. So this will give me a negative answer. Okay, so I can state where I am increasing and where I am decreasing. Okay, we are increasing from -infinity to -1, union 0 to 1. Then we are decreasing from -1 to 0, union 1 to infinity. So there's the first part. Then we need to determine local maxes and local minimums. Okay, so here, increasing to decreasing, we would have a local max at x equals -1. From here, we're negative to positive. So this is a local min at x equals 0. And then positive to negative, that's going to give us a max. So local max at x equals 1. Okay, so there's our information for our answer here. Now we're going to go ahead and switch to concavity. Okay, so concavity of a graph. If the graph of f lies above all the tangent lines on the interval, then it is called concave up, okay, on that interval. If the graph of f lies below all the tangents on I, it is called concave down on I. So here's an example. If we look at example A, if I go ahead and draw some tangent lines in here, you should be able to see that the curve is above it. And since it's above it, this is concave up. The other thing is you guys should be able to look at it and see that it's has like an upward, kind of more like a bowl, okay? It'd be able to maybe, well, not in this case really, hold some water maybe. But this one, there's absolutely inside here no holding water, right? So this case, if I draw my tangent lines, here's a few of them. Notice how the curve is below it. So since the curve is below, this is concave down. So that is concavity. So let's just maybe look at an image where we have to write on there where it's concave up and concave down. All right, so I'm looking here. I would say roughly to about here maybe is where it starts to change. You should be able to see that this is concave down, okay? Or you call it concave down, either way. It has that downward turn to it. And then here, from here to here, I would say that this is concave up. Kind of creates a bowl, could hold a little bit. From here to here, okay, kind of has a little curve down, it's concave down. Then from here to here, concave up. And then I think there's one more little switch here, okay. We would be concave up. And then from here to here would be concave down. So one thing to take note of is that you don't always have to be up, down, up, down. This one is up, and then it continues to be up. All of these points that I created on here, these are what we call inflection points, and we'll get to that. Inflection. And that is when your graph changes from concave up or concave down, or even just it changes concavity. Okay, it's not the same type. See how here it switched? So that'd be an inflection point. So, definition, a point P on a curve is called an inflection point if f is continuous there and the curve changes from concave up to concave down or from concave down to concave up. Okay. The way you can check concavity, is using your second derivative. Okay, if your second derivative is positive, then it is concave up. So here's a nice little picture. Your second derivative, okay, so two positives. And if it's positive, you are a smiley face, okay? If your second derivative, so two negatives, is negative, then it is frowny face, okay? Going downward, concave down. So positive up, negative down, which should make sense. The biggest thing you need to start remembering is your second derivative is concavity. Okay. So here's a picture of some honeybees and how their population increases over time. Okay. So how does the rate of population increase over time? So I would say that it is increasing, and then it increases a little bit quicker, if you could see that your tangent line here, and then it starts to steady off. You might be able to see, and it's not very clear on this graph, but this is a picture where this is probably going to start to kind of level off. It's not going to get very much higher. Does anybody know what that's called? Can't answer me, but it's called the carrying capacity. At a certain point, an environment can only support so many bees for so long, right? Otherwise, there's not enough food and stuff for them to survive. So I would say that it starts out slowly increasing, then rapidly increasing, and then slowly starts to kind of level off as it gets closer to what we call the carrying capacity. When is the rate the highest? Okay, I would say roughly right here. What is that, about 12? Okay, when is the rate the highest, which is basically a rate, is your first derivative. So the rate is the highest at t equals 12-ish, 12 weeks. And then the other thing that's worth noting is, what do you guys notice kind of around 12? Ooh, maybe I didn't draw. My pencil got too big. I'd say maybe a little less than 12. But do you notice how it goes from concave up to concave down? Okay. Well, the rate's the highest when you switch. Okay. So at the point of inflection, I really would say that's a little less than 12. Maybe here, maybe 11. So at that point of inflection is when it's the highest. So when is it concave up and when is it concave down? We're going to go with 11. So we are concave up from, we're going to go 0 to 11. And then when are you concave down? Concave down from 11 to, I guess we'll say infinity. Perfect. So there's example 5. All right, your favorite sketchings. Okay, so it says sketch a possible graph of the function f that satisfies the following conditions. Okay, so what this is telling us is our first derivative is greater than 0, so positive on the interval from -1 to 1. Okay, well, your first derivative refers to increasing and decreasing. So in this case, we are increasing. Okay, from -infinity to 1. So maybe I'm going to make a little note. We're increasing here. And then we are less than 0, which means we are decreasing. What does that mean is happening at a point? If we're going from increasing to decreasing at 1, that means we have a maximum, some form of a max. For sure, local, could be absolute, but then make a note, they've got to have a max here, okay? So that's what that step 1 tells us. Now let's go ahead and look at part 2. What is this telling us? Talking about our second derivative, well, we just got done talking about our second derivative. All right, if our second derivative is greater than 0, so second derivative, two positives, because it's greater than 0, smiley face. That means we are concave up, okay? So we are concave up from -infinity to -2. So I'm just going to make it a little note. Same idea. We are concave up here. And then from 2 to infinity, we are concave up still. Then when our second derivative is less than 0, from negative 2 to 2, we are concave down. And then the last part of information we have is our limits. As we look towards negative infinity, all the way to the left on our graph, we are going to approach negative 2. So I'm going to make a little note. And as we approach to infinity, to the right, we're approaching 0. All right. So I have all my information as best as I can put on here. Now I have to actually sketch the curve. Okay. Got to be concave up, and I have to continue to be increasing. Okay, so I'm going to continue to increase this whole time until I get to here. So we know there's going to be a point of inflection. I know I got to start down here because I have to approach this. So I'm going to be concave up. Then at negative 2, we're switching. So there's that point of inflection. So concave up, then I'm getting to here. Then I'm going to still be concave down, but still increasing till I get to my maximum, which is here. Good. Now, I'm still concave down, so it means there's another point of inflection here, but I got to start decreasing. Okay, so concave down. Now there's a point of inflection. Now I have to be concave up and approach my limit. That would be our graph. So let's check. Do we see our point of inflection here? Ooh, I want to use a different color. Inflection should be here. And it should be here. Yep. And we should have a max here, which we do. And we're approaching our limits. So that would be our graph for example 6. Okay. Just take and decipher each statement, you guys, and try and write down the graph best you can. All right. Second derivative test. Okay. So it says, suppose f double prime is continuous near C. If you find your critical points, okay, and then you plug your critical point into your second derivative and it's greater than 0, okay, that means there's a local minimum. Okay. Why would this be? Well, if my second derivative, it's concavity, we are positive and positive, means we are concave up. And so if I plug in C to this graph and I get out a positive into my second derivative, that tells me that this is going to be a minimum. Same thing with if I take my critical value, plug it into my second derivative. Not positives, we're negatives. Negative, negative, frowny face. That's going to tell me if I plug in C to my second derivative that this is a maximum. Is there other ways you can find it? Yes. But just remember that you can also use this test. Okay, we've figured out max and mins using other methods. But f prime of C, just remember those are your critical points, values. Okay. All right, so I think this is our last example of today. So we're going to discuss this curve with respect to concavity, points of inflection, and local max and minima. So many things. So let's start out with what we know. We know how to do increasing, decreasing, okay, which is going to give us our critical points. Okay, so we're going to take our first derivative. So y prime is equal to 4x cubed minus 12x squared. Then we're going to set that equal to 0. Okay, so we have 4x squared x minus 3. Setting them each equal to 0 and solving, so x is equal to 0. We divide by 4, right? 0 divided by 4 is 0, and then take the square root, and then x equals 3. And technically we'd have plus or minus 0, but there isn't such a thing. So these are our critical points. Okay. Now we're also, since we want to know about concavity, we're going to need our second derivative. Okay, so we're going to do our second derivative. We should have room right here. Yeah. So y double prime. So we'd have 12x squared minus 24x. And then we're going to set that equal to 0. And when we set our second derivative equal to 0, that helps us find our inflection points. Okay, so now I have 12x equals 0 and x minus 2 equals 0. So x equals 0 and x equals 2. Okay, so these are inflection points. And one thing that I start to notice is this number is in both. So is it a max min or is it an inflection point? So we got to actually figure this out, okay? So this is kind of a weird, we're not sure what 0 is, okay? Is it a max, min, or is it an inflection? And the way we're going to figure this out is we are going to make ourselves that number line, and we are actually going to put all of the numbers on here, okay? So we are first going to start out with just doing our critical points, okay? So we got 0, and we have 3. And we are going to plug those, since they came from our first derivative, those intervals into our first derivative, okay? This will help tell us increasing, decreasing. Increasing or decreasing is what this will tell us. So let's do that. Plugging it into here, okay? Number less than 0 being -1. So if I plug in a -1, square it, positive. Positive times 4 is a positive. -1 minus 3 gives me a negative. So my overall answer here is negative. Okay? Then from 0 to 3, I'm going to plug in 2. 2 squared is 4. 4 times 4 is a positive. 2 minus 3 is a negative. So my overall answer is negative. Okay, so now I'm seeing negative, negative. What did that mean in terms of first derivative? It meant I was decreasing and then I continued to decrease. So what that tells me is there is no max or min here. Okay. So my guess is since there's not that, I'm leaning towards an inflection point. But we will continue on and we will find out. All right, now we're going to plug in a number greater than 3 into our first derivative and see if it's increasing here, hopefully, or it's decreasing the whole time and then there is no max or mins. So a number less than, or sorry, not less than, greater than 3, 4. 4 squared 16 times 4, another positive. 4 minus 3 will be positive, so my overall answer is positive. Good. So I am negative, negative, and then positive. So I am decreasing until I get to 3. Then when I get to 3, I'm increasing. So I could probably conclude that we're decreasing and then increasing, so that right here, there is a min. This is decreasing, decreasing. I'm guessing that that is considered an inflection point. Actually, I know it is. All right, now we're going to go ahead. The new information, this is kind of old information. Now, the second part of our notes was dealing with concavity. So we're going to check our inflection points, okay? So that's 0 and 2. So now I'm just going to use those numbers, okay? 0, I'm going to put 2 right here. And I'm going to check those intervals, okay? And since this information, 0 and 2, came from my second derivative, I'm going to test my intervals with my second derivative. Okay, so I go ahead. If I plug in a number less than 0 into my second derivative, -1, this would be negative. -1 minus 2 would be negative. So I'd have negative, negative, which would give me a positive answer. Okay, positive second derivatives, remember, we are concave up. Now I'm going to do in between 0 and 2. Okay, in between 0 and 2, we will plug in 1. 12 times 1 is 1. 1 minus 2 would be, so we got positive, and 1 minus 2 would be negative, so my overall answer is negative. Remember, negative, negative is frowny face, so we are concave down. And then our last set from our second derivative is from 2 to 3. Okay, so a number, sorry, not from 2 to 3, 2 to infinity, the whole set. So a number bigger than 2, we could plug in 3. 3. Positive, 3 minus 2 is positive, so it would be positive, positive, which gives me happy face. And remember, this is basically what that theorem, or not theorem, but the second derivative test tells us. If you plug your critical value into your second derivative, it's positive, it should be a min. Does that support what I did? I plugged in 3 to here, I got out a positive number, and so it's telling me I should have a minimum, which is true. Okay, so what do we all have here? We need to discuss the curve with respect to concavity, points of inflection, local max and min, and then use this information to sketch the curve. So I would say my concavity, concave up from negative infinity to 0, union 2 to infinity. And we are concave down from 0 to 2. Points of inflection. My inflection points are 0 and 2. Got those here. And then we are supposed to sketch the derivative, or sorry, sketch the curve. We're going to sketch the curve of the original function. So to provide a little more room, we're just going to copy this. I know maybe if you're writing on paper, probably you can. Make this a little smaller. And then we're going to sketch it, kind of like using the information we had on the last one. So I'm going to go ahead and put on all the numbers, so 0, 2, and 3. And then just to make it a little easier, we were concave up until 0. Okay, so I might just go up, concave up. Then from 0 to 2, we are concave down. And then from here, we are concave up again. And I know that at 3, at somewhere on 3, there's got to be a minimum. And we are decreasing this whole time. And then we are, from this point on, increasing. So I need to sketch a curve that makes this happen. So we have to be decreasing and concave up. Okay, and then I'm going to switch to concave down. So there's an inflection point here. So let's go ahead. Decreasing, concave up. I can make this happen. Decreasing, concave up. Then I get here, and we're going to switch to concave down, but still decreasing all the way till 2. I'm going to run out of room. Should have brought this over a little more. Then when I get to 2, I'm going to switch to concave up, but I'm still decreasing. So I'm concave up, kind of switching here. And then at 3, we got our minimum, and then we are increasing. My graph got really wide. So decreasing, concave up. I agree. Here's my inflection point. I probably would have drawn this graph a little more this way to make it easier. Then I can clearly see that this is concave down. Then I switch again to be concave up. And then at 3, we should be our minimum. And then we are increasing. So that would be a little sketch of our curve that we could have going on here. Maybe I can highlight it with a better color. There we go. So there would be our curve. Okay. So lots of things to take into account. Make sure you refer back to it. Important pieces is your first derivative tells you whether you are increasing or decreasing. First find your critical values and then make your little table and you can plug those numbers into your first derivative. That helps you figure out increasing, decreasing. Second derivative set equal to 0 gives your inflection points. Inflection points are when you change from concave up to concave down or vice versa. And then if you plug numbers into there, they'll tell you if you're positive, you're concave up. If you're negative, concave down. Think about smiley face, frowny face. And there is kind of how all your derivatives affect the shape of your graph. Okay? Lots to take in. Do your best with the homework. Okay? Get a few days to work on it. Feel free to look up other resources if needed. Feel free to message me if you have questions. Otherwise, have a great day. Here is your homework, and I will talk to you later.